So this is the title of my talk. First of all, I want to thank my co-authors, Giuseppe Rosi and Professor Longo, and a special thank also to Professor Dell'Isola, who helped us with the idea of this model. This is the outline of my talk. First of all, I want to build a meta-model of non-conservative piezoelectric controlled system. Then I will show you the failure of an identical, so a particular choice of the meta-model of an identical piezoelectromechanical system. Then I will build up a linear analysis, and I will define control strategies. If I have time, I will discuss also a post-critical analysis. So we consider an autonomous piezoelectromechanical system, PEM, which in its reference configuration occupies a region omega of the space, spanned by the coordinate S of boundary gamma, spanned by the coordinates sigma. So the state of our system is described, but in the reference configuration, at the current state, is described by the displacement vector u and the flux linkage vector psi, together with their time derivatives. First of all, we neglected any dissipation and or energy input. We are able to write the Lagrangian of the system, which consists in three parts: a mechanical part, an electrical one, and a piezoelectric part. Here you can see the contribution of this part on the kinetic energies and on the potential energies, and you will see that some matrices and the differential operator will appear in the formulation. Then, as it is usual, we neglect the mass of piezoelectrics, and we neglect also their stiffness with respect to the stiffness of the structure, and we build the action functional, whose first variation, delta H, consists also of three parts: the mechanical one, the electrical one, and the electromechanical one. And you can see that I will skip the details. Okay, then we used the extended Hamilton principle in order to take into account non-conservative effects, both in the mechanical part and both on the electrical one. And you can see that delta W is the work spent by the non-conservative actions in the T1, T2 interval. Okay, we will talk about damping effect, D matrices, and gyroscopic effects, so-called gyroscopic effects, H operator. Okay, from the stationarity of this functional, I forgot that the brackets indicates the scalar product in the complex field. So, from the stationarity of the first variation of the Hamiltonian, from the stationarity of the Hamiltonian, we can write the field equation of the PEM system and the boundary condition. And you can see that the coupling, both in the field equation and both in the boundary condition, is made by an operator, a gyroscopic operator, and it's a joint, which is defined by the star. Okay, then we choose a particular meta-model, and we call it identical PEM. And you can see that it is defined by equal own characteristics, so we choose an electrical mass identical to the mechanical one, the same for the stiffnesses, and the same for both differential, both boundary terms. Moreover, we choose also equal damping characteristics and equal external action characteristics. So, at this point, thank you. So at this point, we ask ourselves that we can say that identical passive distributed controllers represent usually the best choice for maximizing the energy exchange between mechanical and electrical parts. However, their effects on stability seem to not be explored when non-conservative actions are taken into account. So we ask ourselves, piezoelectric identical controller, is it possible to use such a controller in presence of non-conservative laws? Can it have an incremental effect on the stability of the controlled structure? So here I will skip a lot of details, but in order to perform a perturbation analysis of the PEM system, of the metamodel, we first consider it a purely mechanical system. So these are the equation of motion and the boundary condition. There is a trivial equilibrium. We need, for the perturbation analysis, the right eigenvalue problem, and the eigenvalue lambda naught, which is a function of a load parameter mu, decides on stability, so that if mu is equal to 0, the real part of the lambda naught is less than 0, but when mu reaches critical values mu naught greater than 0, so it can occur an bifurcation condition. So we need also the left eigenvalue problem, the left eigenvectors, in order to write and the compatibility or orthogonality condition. Then we consider the PEM system, the coupled PEM system by a coupling parameter gamma. These are the eigenvalue problem, and these are the boundary condition. Mu is fixed at the uncontrolled critical values, mu naught. Gamma is taken small, with the meaning of epsilon variable, which is a small perturbation parameter, and then we perform a standard series expansion of the eigenvalue and eigenvector. We write the perturbation equation, and we take, at the leading order, lambda naught is a semi-simple eigenvalue for the PEM system. At the epsilon order solution, we have an eigenvalue problem in the correction lambda 1, correction to eigenvalue lambda naught. And we can discuss this eigenvalue problem, and we can see that only in one case, which is when the product of G1, G2, which are complex coefficients, is only in this case, only in one case, when this is real and positive, the two roots of lambda 1 are purely imaginary. This entails that only in this case the identical controller does not affect the disorder, obviously, does not affect the stability of the PEM system, but in the other case it is always detrimental. Okay, let me show this result by an example. We consider a planar Euler-Bernoulli viscoelastic beam, externally damped, loaded by follower force and dead load. We have a Kelvin-Voigt constitutive behavior, and we have a layer of distributed piezoelectric on the beam, and a circuit, a controller. Then these are the three first variation: mechanical, electrical, and electromechanical. When you set some electrical parameters in this way, you can obtain the identical PEM beam. Okay, these are some parameters: alpha internal damping, beta external damping, mu is the load, mu c is the conservative part, the dead load. Okay, gamma is the coupling parameter. So, this result is the exact linear stability analysis of the beam. You can see that the OPF curves in the plane non-conservative versus conservative loads shift. Okay, so the stable zone, which is the gray part of this diagram, reduces itself. And these happen both for the overdamped system, both for an underdamped system, for each value of the coupling parameter. Okay, and if you choose the electrical parameter not perfectly identical to the mechanical one, so you introduce a small imperfection in the electrical parameters, you obtain again an eigenvalue problem by a perturbation method in the lambda one, but you can see that this imperfection appears on the diagonal of this operator, and so if you take them equal to 0, you have a detrimental effect on stability. But if you take them of an appropriate sign, you can entail restabilization of the system, but it could be proved that their contribution is in general small. And I will show it by an example. So you introduce the imperfections and you say that, sorry for the resolution, but in both overdamped, both underdamped system, you can see that this area of stability is very small. So in order to define some different control strategies from the identical PEM, we discretize the system, so the differential operator K and H become algebraic, and we fix these matrices in this way. We recognize three electrical parameters, nu, K, and Xi, and in looking for a control strategy, we want to explore the set of non-similar, non-identical, I can say, piezoelectric controllers for which the non-conservative load, electric load, is taken equal to 0, and the mechanical load, mechanical non-conservative load, is taken equal to the critical load value. The task is in maximizing the amplitude of the electrical oscillator, and in order to do this, we perform a straightforward expansion of the eigenvalue lambda naught. And we look for the singularities which make the electrical response infinite. I will skip the details. I just underlined the structure of the perturbation equation. At the leading order, the mechanical oscillator is undisturbed. At the epsilon order, the mechanical oscillator forces the electrical one. At the epsilon power 2 order, you have that the electrical response influences the mechanical one. So this is the electrical amplitude, and you can see that here, by this equation, you can have three possible control strategies in order to weigh J tends to infinity. The first one is a non-singular but resonant controller in which the electrical stiffness is of order 1, the electrical mass is of order 1, and their ratio is tuned to the frequency of the mechanical oscillator, while the electrical damping is small. This resembles the TMD with a large mass, the tuned mass damper with a large mass. But you can have a singular non-resonant controller for which the electrical mass, the electrical stiffness and the electrical mass are of order epsilon, the ratio is not tuned, and the damping is also small. This is a kind of NES, nonlinear energy sinks, but here we have a controller which is linear. Then you can build up a singular resonant controller for which electrical stiffness is of order epsilon, electrical mass is of order epsilon, and their ratio is tuned. This is a TMD with a small mass. So we perform a perturbation analysis for these three controllers. I will skip the details. At the leading order solution, you have that for the non-singular controller, the mechanical and electrical responses are of the same order. For the second controller, the electric oscillators behave as passive, driven by the mechanical one. And for the third controller, which is defective, the electrical response is larger than the mechanical one. Okay. By equating to 0 the real part of the eigenvalue, you can obtain the boundaries of stabilities for the three controllers. Okay, this is just an example of the previous being discretized via Galerkin procedure. This is the stability domain view from the stable part. So this is the stable part for the first controller. This is the stability domain for the second controller. This is the stability domain for the third controller. If you make a comparison, you can see that the singular resonant controller is the best, because it can increase the critical load of about 60%. Okay, when just 1 minute to conclude, when you take the nonlinear model of beam, when nonlinearities are of geometrical and inertial type, you can perform via the multiple scale method an analysis of the nonlinear post-critical behavior. These are the results for in terms of complex mechanical and electrical amplitudes of the multiple scale method, which contain the sensitivity of eigenvalues, obviously. We study the steady-state solution in terms of a real mechanical amplitude, and you can see that for the three controllers, the limit cycle is less than the uncontrolled one. Okay, these results are confirmed via direct numerical integration in the three cases for a two degree of freedom system. Okay, these are the conclusions, but I have no more time, so thank you for your attention.
I know that at Linux you have some equipment to consider such system. Do you build some fans?
Yes, we are trying to work with a discrete model. In particular, we are thinking to perform an analysis on a double pendulum. The actual problem we have is to model, to experimentally realize the follower force.
Okay.
Okay. Yeah.
Questions? Thank you again.
Thank you.